Hello and welcome to TidyX, episode 11. Alright, so TidyX is a screencast where we go through and try to explain our concepts and where we go through and highlight Tidy Tuesday posts. My name is Ellis Hughes. I'm a statistical programmer at Fred Hutch Cancer Research Center. You can find me on Twitter at Ellis_Hughes.
And I'm Patrick Ward. I do data analysis in sport. You can find me on Twitter at OSPPatrick, and you can find the both of us on Gmail. If you have questions or comments, you can send those to tidy.explained@gmail.com.
And we do keep track of that. We do look at it. We've gotten a few emails, and thank you for those of you that sent those in. It's great to hear from everybody, or hear from y'all, what you've been liking. And how you like to see this. It's great. So, all right, moving forward. So this week's Tidy Tuesday data set is beach volleyball. And so it's a pretty large data set. I think number of people had a good fun. I know Patrick and I had a lot of fun going through and scrolling through and looking at everybody's submissions. Patrick had a lot of fun, going through and exploring this data set.
Finally a sports one. We got a sports. Yeah, it was a good one.
It's right in his wheelhouse. The Tidy Tuesday post that we're going to be discussing this week is from Eric Ekholm. Hopefully I said your name correctly there. But we thought this plot here was just super cool. It was super clean. It showed some pretty cool concepts. You look at it and you immediately understand what's going on. You don't need to understand more. You don't, but like external stuff. But you're really able to look at this and start seeing trends. You can see the way that the two players worked well. I mean, Kerri and Misty are some of the best, or they were the best. They are the best.
Yeah.
Still, like if you look at their win percentage, they're the best team.
Yeah.
And most number of games and whatnot. But you can see how their skills complemented each other. Just quickly looking at this, you can see how long they played. So Eric, this was a super great data viz. So we reached out to Eric. He's linked to his code here, so it's on GitHub. We'll have a link in the description, and so this is his code. So why don't we take a second and step through all that? All right. So let me zoom in a little bit so y'all can read it clearly. All right. So like we've discussed, he has all his libraries at the very beginning. He's using Tidyverse. He's loading that first. And Janitor. Janitor's back to help clean up stuff. ggtext. Seen that before. It helps with plotting text. Lubridate to handle dates. This RCPP role, which I hadn't used before, but Patrick said you have, right?
Yeah, I use this pretty frequently, actually. I mean, anytime, like dealing with time series and you're trying to do rolling statistics over data sets where things are collected in serial measurement, or like even like wearable tracking data, things like that.
Mm-hmm.
Super useful.
Yeah, that makes sense. And then extra font to help and bring in some extra fonts, like its name says. One thing that we thought was really cool that we hadn't seen before was Eric was setting his colors at the very beginning here. So he can go back whenever he wants to and, just quickly update this, say he wants to change the color. I don't know what that'll actually end up being, but he can go through and just change his hex code. That'll change his plot later on. So he's got this really nice finite control at the very beginning. He's defining that for himself at the very beginning. All right, so let's load in the data set. All right, now that went quickly. All right, so you can see it's a pretty large data set. I think you have to guess max. So this then tells read CSV and read R to not try to guess the column type until it's read 76,000 rows. So it's pretty large. Let's see now. Let's just do what would be dim. There we go. Dim VB matches. Yeah, 76,000 rows and 65 columns. So we got lots of data here, lots of stuff to explore. All right, so the first thing that Eric does is after he's got VB matches here is he uses this function matches. So matches is a helper function. It's a tidy helper. So what it does is you pass a regular expression. So regular expression, they're kind of weird to explain, but it's basically it's keywords to search for patterns. And so what he's doing is using the function matches, look for any columns that have the word rank in it and remove it. So that's what that negative is doing there. So he first removes any columns that have the word rank in it, and then he's renaming W player to be W underscore player 1 underscore name. Same for player 2. Same for the losing players. And so this is, I think, to kind of be more consistent with how the other statistics... Oh, I need to load all those in. That's helpful. I'll run that too. So I'm assuming he's doing that so that it matches some of the formatting, with the other statistics that exist. So because it had a different format. So then he goes through and does a mutate. So he creates an ID variable. So he's using the function row number. And so this then just assigns the actual row number to the field ID, because Tibbles do not have row names, which I think is an interesting concept. I think Hadley and that group there has some opinions about whether you should be using row names or not. I don't think they should exist, so that's their way to get around it. Next, he's using a mutate at, which I think will actually be going away in the next version. Well, not going away, but there'll be a different way to be using mutate where it uses across, but that's not available yet. What he's doing is finding all the variables that are not the ID column and converting them into a character value. This is just for consistency to make his life easier, because what he does next is a pivot longer. So what he does is, all right, for all the columns that have a W or an L at the beginning, W underscore or an L underscore, pivot them longer. So make them from being a wide column or a wide data frame into a long data frame. Set the names to be the name of that column, and create a vector or a field named name, and then the values of those vectors or fields to be in the field vals. I don't like this wording. Pivot longer. Like my brain
it never makes sense to me either. So.
I got used to the gather and spread nomenclature, so this stuff my brain just has some difficulties with. Next, he goes through and does a separate. So he uses the field name. So he just generated that with the pivot longer, and he's going to create these new fields: winner, loser, player, and key. And so name has these values. Actually, let's just quickly run this so that we can do a quick head, so y'all can see what that looks like. Will it run? It takes a little bit of time. All right, still wide. So let's just do a select on name and vowels, just to make it a little bit smaller. Right? So what he's doing is separating on this field name, so we can split this out into winner, loser, player, and key. Split on this underscore here, so then winner, loser is populated by this first value here. Player is populated by P1, and key is name, birth date, age, so all the various statistics and whatnot that exist. So that's now all spread out into it. So now he runs all that. Then he does a pivot wider. So from key, which is the P1, the statistic, make that wider with the values that exist inside this. So that now what he's doing is he's trying to create a data set that is one row per player per game, I believe.
Yeah.
Right. Yeah.
Yeah. Yeah. Mm-hmm. With all the stats across that game, including in that name column, including the vitals, so name, birth date, age, height. Yeah. Mm-hmm.
Boy, that's some pretty tricky manipulations there. That's pretty smart. And then what he does is that he is curious about Misty, May-Treanor, right? And then Kerri Walsh. So that's what he's doing here. He's using the str detect from the stringer package, and he's filtering to keep only Misty and Kerri. So this is another example of a regular expression where find Misty or Kerri Walsh.
Yeah.
All right, so now it's running through. It's going to take a little bit of time to chunk through all that data. Created some new column names there.
And this is necessary for his plot, because what he's going to have is a row for every game for Misty and a row for every game for Kerri. Whereas when the data originally came in, they were meshed together as a team. It would have been Kerri, Walsh, Jennings, and Misty May-Treanor if we were to look at the original data set. So
yeah,
he's basically turned this into a data set of Misty May, 1 row per game, and a data set of Kerri Walsh, 1 row per game, and then he's pushed them together, one on top of the other.
Yep. All right. So now he's got this MK table, or make table, I'm going to call it from now on. It's still actually fairly wide. I think that's, just he kept a lot of information, and there's a lot of statistics that are available. Converts the date into a date object, then removes any rows where total attacks is not NA. So what this does, and he actually put this really, really nice comment in there, is that's going to remove any rows that are missing information. So you don't want to have data sets that, or don't want to record any batches that don't have any information in them. That's not useful. So then he does this pivot longer again, but this time any fields that start with tote underscore, pivot them longer.
To stat.
So all the column names go into the column stat, and all the values go into the column vals. And then he's going to remove any cases where vals are NA, rearrange by date. So that's what that arrange does. And so this will be increasing. So the older dates, so like 2014 will show up before 2015, for example. So he's going to arrange that. Then he's going to, so this is, I hadn't actually seen this before, and Patrick and I are going through this, but this group indices is kind of a way to do a group by without actually creating or doing a group by within it. So it's going to label the indices with this new ID based on date and match number.
Yeah, it's basically just a sequential row ID, 1, 2, 3, 4, all the way up to N.
In this case, at least.
Yeah, in this one, yeah.
And then remove all. So in the name, remove cases where there's a space. And then any character. That's interesting. I'm not quite sure what that one's doing. Then convert the statistics back into a numeric. And then what we thought was pretty cool, and what makes this plot work here, is what he does an if else. And then if it's a Kerri, so if it, what he did was keeping, so what this is doing is letting them keep their first name. So it's either Kerri or Misty. Yeah, that's what he's doing. Keeping names, so it's only Kerri or Misty. And then if it's Kerri, he's multiplying it by a -1. Otherwise, if it's Misty, it stays as her statistics.
Yeah. And that's where you get the up and down plot. He inverts Kerri.
Yep. And then select, so he's now removing player, birth date, age, and height from the data set. Group by the player and their name, and then here's where that RCPP roll comes from. What he's doing is calculating some rolling averages. Patrick, maybe you want to take a second to talk about that?
He's going over that vals column, and the N is basically setting the parameters, the workhorse of this. So he basically wants a 10 match rolling average. So for every vals column, it's going to look back, and it's going to look back over the past 10 and then deposit the previous 10 average into each subsequent row. NARM, obviously false. We know what that means. If there's an NA, it gets removed. The fill there you can set to lots of different things. So you could set it to NA. The align right would basically be telling this function that you want leading NAs, for example. So the first 10 rows will be NA before you start, before you see a value deposited. You could do fill equals 0 if you had a reason to to do that. There's lots of different things that that could go in there after the fill. But basically, what the fill means is it's basically telling roll mean function how to handle the values that are not in, the leading values or the trailing values. If you did align left, I think will take away the bottom 10. So
yeah. All right. So then he's defining a few more bits of information for the plot, where he is setting the labels to be, okay, what is the maximum minimum date and converting into a character. Otherwise, it's actually a numeric value. Dates are kind of a weird class. And then he's setting the breaks to also be that range as well. So they only show up at the beginning and end of the plot. He's setting his family to be Bondschrift? I don't know, to text family then. All right, so one thing that we've discussed a fair amount in TidyX is, doing a few manipulations right before you send it into the plot here. You've done your massive cleanup already, but you're still kind of fiddling around with a few things, and that's fairly common here. And typing makes it so easy to be doing that right before you plot it. And so it looks like what Eric did here is he's going to keep all the statistics that are kills, aces, blocks, or digs. And so that was the str detect there with the filter. And then what I thought was interesting here is he's doing the str replace all from the stringer package, which I think is a hugely helpful function. I wish I remembered it more when I'm doing my string replacements, because it allows you to apply multiple regular expressions at once. But what he's doing is finding any places in stat where it's total kills and replacing it with a capital K kills, to aces with capital A aces, to digs with capital D digs, to blocks with capital B blocks. What might have been a little bit clearer here, because he's replacing that entire string, would be to be using a case when. So you could do case when stat equals tote kills tilde kills, stat equals tote aces tilde aces, just to be a little bit more explicit with what you're trying to be doing here, because here you're relying on the regular expressions, and regular expressions can get messed up, and that would then just be a little bit more clear. Next, he's throwing into ggplot2, into ggplot. He's defining his aesthetics at the very front here, which is a way that I like to do it as well. So that way it gets applied to all the other geomes. In this case, he only used one geome to make this plot. And so I thought that was really cool how he was able to make such a really, really interesting plot using such a simple geome. I mean, kind of else how you look at it. Then he does a facet wrap based on the statistics, so that it kills aces, blocks, and digs. The y-axis can then be free, so it'll scale up and scale down based on the true value within that statistic. And then ncall equals 1, so that means it's going to be stacking vertically. Otherwise, it would, I think by default, ncall is 3, so it'll do 3 plots in a row and then a fourth one down the lower left. It looks kind of funky. He didn't define harbor themes the beginning, but this is how you'd identify a package that you maybe have loaded, but didn't load into the namespace here, and you want to use some function from it. So this is, it's a practice that a lot of people do. Defining his labels, he's wanting X and Y to be blank. Great title name, America's Dynamic Duo. With the subtitle, what he's doing is he's combining some HTML styling, which I think is a new feature in ggplot2, with some markdown styling. So he's making that, I think, bold or italic. I don't remember what double star means. So he's going to
bold is double star.
Bold is double star. There you go.
I think singles are italic, yeah.
So
we're about to find out.
Yeah, we'll see in a sec here. So he's setting Kerri to be this color here, and he's setting Misty May-Treanor to be this color here. And then BR in HTML means go to the next row. And then he's adding his caption where he got the data and who created that viz. So Eric, super, super great. He used scale fill manual, so he's defining the colors he wants to be using. So he used blue and red, which he defined at the very beginning of his script there. He's using scale x continuous to tell the ggplot where he wants his breaks and labels to exist, and those were defined by the date ranges that he has and the values that he had.
The range of the number of matches.
Yeah. So he actually put this comment here, but he was using scale y continuous where he had 3 breaks, and ABS, was that defined? Oh, he's taking the absolute value. Oh, so this way it flips across the y-axis. But because he now doesn't have any y-axis text, he's actually saying this is a little bit superfluous. He's defining his themes. This is where the sand color that he defined earlier in the family that he defined earlier comes
clever
from.
Use of the sand color.
Yeah. So he's setting the background of the plot to be that color.
Yeah.
He's setting the text to use the new family of text that he defined. Same with plot title, subtitle, plot title, position, plot. Oh, so that's like within the plot, I guess. Strip text. So he's defining how the text for each facet should be defined.
Yep.
He doesn't want there to be a legend. This is the panel spacing, so the spacing between each facet. And then he doesn't want, so element blank is telling ggplot that you don't want any of these. He doesn't want grid lines on it. He doesn't want the axis text on it. So all right, let's run that.
Take a look.
Badoom, and there we go. Oh, it's because I'm all zoomed in. Here, let me
zoom it.
Throw that over here. All right. So there you go. That's his great visualization. Like we were saying earlier, it's kind of cool to see, the difference in like the styles of plays. Like Kerri's doing a lot of the blocks on the team. Like she's a very defensive. Misty's got a lot of those digs.
Yeah.
And all that, and then you can see some periods where they're still active, but one of the others weren't playing. So I have to guess that one of them was out for an extended period of time, or at least extended period of matches.
Yeah.
For one injury, life events, something like that. And then I think this is the end when Kerri went to the Olympics for the last year.
Yeah, she took on another partner.
Yeah.
Yeah.
So I remember
but
that.
Still won.
Yeah, of course.
Yeah.
So good. So yeah, that was a super great viz. Took us through some fun skills to try out. So thank you so much, Eric, for letting us go through and explain your code.
Yeah, really cool one. Love that.
All right. So now we're going to go through and explore this data some more from, let's restart my R session so that we're clean. Scroll up to give you a little bit of dizziness. So take you through, Patrick, exploring some of this data with my inputs as well.
Yeah, I thought it'd be cool to look at this. Since Eric had a time series, I thought, well, we could look at time series 2 and just do it in a bit of a different way. So similar to all of the code, we express our packages up front there. We've got a few of them, and we set our plot theme to light. We load the data in using Ellis's handy dandy R package for that.
Tidy Tuesday R.
Yeah. And it also has this cool little README there where we can actually get the Tidy Tuesday web feed right there in our viewer. We're interested in the VB matches data set, so we'll call that explicitly from the various, there was a number of data sets in this week. And this is the one that we just saw. So it's like, 76,000 long and 65 wide or something like that. There you go. Yeah, pretty close. Okay. So the first thing that we wanted to do here is we're curious about teams over time. So a time series of actual teams, whereas Eric looked at individuals over time, even those individuals were 2 players that for a consistently long period of time, I think 800 some matches, made up one team. We want to look at teams collectively. So the first thing here was to create ourselves a data set that basically allowed us to look at each team over time, whether they won or lost. So Ellis, why don't you go through a little bit of the data pre-process here?
For sure. All right, so you're taking the VB dataset, which is the VB matches here. I'm using this row-wise. So this is a feature that's been a little bit neglected, or they've feelings about it have come and gone. But what it does is it's basically it's a group by, but it's for each individual row. So this allows you to do this mutate here in a slightly different way than you might normally do it. So the data set that as it came in, W player 1 and W player 2 were listed. You're scratching a little bit there, Patrick.
Oh, sorry. Dragged on the desk.
It's all good. All right, so W player 1 and W player 2, and same with L player 1 and L player 2, were listed alphabetically. But I've come across cases where they aren't, how W player 1 and W player 2, even though it's the same two players that are playing, can be flipped back and forth just based off who entered the data in. And so by doing it row-wise, what we can do here is use C to create a vector, so W player 1 and W player 2 for each row, and then do a sort. And so what this will do is make sure that it's always listed in alphabetical order. And then when you call a paste using collapse, so paste will then execute whatever pasting it needs to be doing on whatever you've entered here, and then performs a collapse, so it'll then join the vectors together using whatever value you list here. So like you can do, I think when Patrick, stop going up. So you could do paste C test 1, test 2. If you just throw that into a paste, it's left alone. If you then list because paste is vectorized, so then you can do ungula, like ungula gungula from Groundhog. Bill Murray.
Mm-hmm.
So if you do a paste like that, it's going to paste together this first vector entry with this first vector entry, this second vector entry with this second vector entry. But then if you add in a collapse, what it's going to do is going to take that output from these two and paste those together with this delimiter, or I guess not delimiter, but separator.
Mm-hmm.
So if you run that in, it's now going to put in that comma in there. So now it's going to return a single string of those two values. And so that's what we're doing here. Thankfully, they're always listed in alphabetical order, so you could just do it with a paste and sep, but this was more of a cover yourself situation in case things aren't listed the same way every time. And then you can also do the same here with the mean, because we're using row-wise. There's not a parallel mean, so this is a way to do that and remove any cases where NA. Then you're going to subset to select only some values that you care about. So we're going to use that same matches that Eric used earlier. So this is going to keep any columns that contain the string team, or contain the word team within it. So it's not just a team, just like those 4 characters in that order. And then with ends with, this is another tidy helper. It's now going to find any fields that end with the word rank, or end with those 4 characters. And so you could also have done that with a matches, and the regular expression for end of string is $, but this is a little bit clearer about what you're trying to do, and it's a nice helper function to do that. So we're going to execute that. It's going to take a little bit of time. Row-wise is a little bit less efficient because it's not vectorized. But there we go. We've subset to only keep this sort of data here. All right. What's next?
Cool. All right. So now we're, let's see, what did we do here? Creating the success data set. So we take that team outcome data that we just, or we're creating a team outcome data frame from teams. We select a few of the key columns that we were interested in. We didn't end up using all of these, only a few of them, but we wanted to make the data a bit smaller. And then we go down, we use this gather function here. Mm-hmm. So we've got a key called outcome. which is going to provide us with the outcome of the match, win or lost, and a value of team, which is going to provide us with the team name, which Ellis just created above using the row-wise function that we just went over.
Mm-hmm.
And then after that, we do a little mutate where the outcome, we're just going to use a gsub, which is a handy-dandy function here when you're dealing with some strings, where we want to remove the outcome would actually come out as being W team or L team. We're just going to chop off the underscore team tag at the end of each of those. So we're left with a basically a column of W's and L's, wins and losses.
There you go.
There we go. So now we've got gender, the date of the match, the year, the match number. So that's a ID kind of sequence, or no, that's from the matches themselves. The outcome, and then the team name. All right. So now I think we are ready to do a little bit of exploratory data analysis.
Yeah.
So first one. We just do a simple count like we've done in many of the previous ones. We count the teams. So there we see Kerri Walsh, Misty May played 846. They lead by a mile, over 200 more games, almost 200 more games than Dahlhauser and Rogers. Obviously, those are two teams that were perennial gold medalists for a while. Mm-hmm. We do a cool little plot here. I thought this was really nice way of showing the time series initially of the win percentage. So Ellis does a rolling win percentage here. So from that team outcome data set, he's grouping by team. We only filtered out those that played at least 200 matches. So obviously we're sticking with kind of the cream rises to the crop there, the ones that have really stuck with it for a long time. Arranged by date and match number so that it's properly arranged when the plot comes out, because it is a time series. So date order actually does matter here. And we create a few new variables here, the cumulative win percentage, so their win percentage over time, which is basically wins divided by n matches that have been played. A rolling win percentage, which is a cumulative sum of the outcome win divided by the sequence of 1 to n, so rolling over time. And then game numbers. So this is basically just a simple index that's a sequence. The first value there is the from, so we're starting at 1, and the second value or argument is the 2, which in this case, the n with parentheses is basically just counting rows for our specified group by, in this case, team. So it's arranged by date, and it's just going to take the first date and give it a 1, the second date a 2, all the way up to n dates for that team. And then you add the ungroup there just to be safe as we move on. So there we go.
Yeah.
Cool.
So we've just now added a few of these new columns here. So this rolling win percentage is just looking for total number of games they've played so far. What is their win percentage? Cumulative win percent is given their entire career. How many games did they win?
Right. Yeah. Exactly. We weren't sure which one we were going to plot. Actually, we'll plot the rolling win percentage here. If you're interested in the cumulative win percentage, there will be a plot below this that we just won't go over for time's sake. But it's a standard geom call plot that we've done a million times that is on the male data set.
Yep. So what we're going to do here is take the team win percentage here. We're only going to look at the women's volleyball teams. We're going to group by team and figure out which were the top 5 teams. So first gets us the first entry, basically, in cum win percentage, because this is just repeated across everything. And then what were the total number of games they played. We weren't quite sure what we were going to do with that yet at that point. Take top n, so which were the top 5 teams based on the cumulative win percentage, and let's arrange them by cumulative win percentage, but start this desk or descend function tells arrange to order it from largest to smallest, because by default arrange will do it from smallest to largest. So amazingly, well, not amazingly because we kind of already knew this, but Kerri and Misty, not only did they play the most games, they won the most.
Yeah, wow.
So
Tough to beat.
they played a lot and they won a lot.
Yeah.
All right. So what we do next is we use that team win percentage, just that cumulative winning percentage here. We're going to filter to only keep those top 5 teams. So the in is allows you to do multiple comparisons between the team and the top wins W team, which is the 5 teams there. We're going to order it to make sure that it maintains that same order that we have here, just for visualization reasons. Next, we throw it into our ggplot. I guess I did some. So what I did here is I defined my aesthetics within the geoms, and this is because I had multiple data sets going into this plot here. So we create our ggplot, then we create a geom line where we define our aesthetics as the x is the game number. So that's the index basically from starting at 1 and it goes to the total number of games they played. Y is the rolling win percentage. So this is for given the total number of games they played, what is the win percentage that they have? We're going to group and color by team. So this means the group is telling the geom line to draw the line for that individual team, and then I want to have color by each team as well. We're going to add a point to it as well, but this time we're going to use top teams W, which is the super simple or super basic data frame. So what I'm going to do is now draw a point at n games at the cumulative win percentage, because this value should match. Once we hit n games in our line, this value should match the rolling win percentage.
You would hope.
Yeah, if it doesn't, we've got something wrong. And then we're going to color by team as well. Next, we're going to add this geom label repel. So this comes from the GG repel package. Sorry to scroll up there and make you a little bit dizzy if that happened. But this kind of adds a nice feature to label where it'll do its best to not overlap your label. So it will automatically check to see if you're overlapping, and if it does, it'll try to shuffle them around a little bit so they don't overlap. So we're once again defining data as top teams W, so top teams women. X is n games, Y is cumulative win percentage, and the label that we're going to be drawing into that is a scales percent of the cumulative win percentage. This nudge X and nudge Y is telling it randomly move the the label around on the x-axis by some value. But nudge Y, you'll see this in a second, but there's a little bit of space above the top lines and a little bit of space below the top teams. So I did this case when, so that teams that had a winning percentage greater than 0.85 would, their labels would be listed above the top 2 lines. So there are only 2 teams that had that, and then the other teams, teams that had a winning percentage greater than 0.8 and had greater than or less than 300. So this is getting rather specific into the actual inner workings of the plot itself to figure out where things should go. So this took some trial and error. We're going to set our Y scales to be labeled by the percent. Our x-axis is game number. Our y-axis is win percentage. Title is career wins, and the subtitle is top 5 win percentage for teams with at least 200 matches. We're setting our theme. We're defining how the text should be and where the legend will exist. And then I used this new this guides function from ggplot to tell it I want it to be showing for my color legend at 3 columns by 2 rows. So I'm just telling it how I want the legend to appear. So run that. Oh, still I gotta run wplot.
There it is.
Give it a second. All right, there we go. So as you can see, I've got the 2 up above and these 3 a little bit further down there. And so then, as you can see, 3 columns, 2 rows by row. And so Kerri, Walsh, and Misty May listed all the way out here with their 92% number of win percentage with, over 800 games, just legendary. But as you can see here, even with them, like that win percentage, it can fluctuate so much in the beginning before it levels out, before you can truly see, they are a really good team. But if you were to look at them in their first, what would that be? First 10, 20 games.
Yeah.
They drop down to, under 70% win percentage, which, there's not many games at that point, so you don't really have much of a true
Even
sampling.
through the first 200, they're still kind of climbing,
Yeah.
before they hit it. And then like a blue team like Elaine Young and Holly McPeak, they started out really hot, and then, again, over about 150 or so matches, they start to level out. The purple team, Elaine Young, they're going through, and then at about 150 matches, they start to level. There's actually ways you could calculate where a team starts to stabilize and make a decision on whether you've seen enough games to think that they're a good team. I think in psychology they call it split half reliability, if my memory serves. But there's a way of calculating this.
Interesting.
Yeah.
All right. So we're skipping over some the GM call plot that we've discussed ad nauseum.
Yeah.
So next we're gonna
Okay.
talk about a little bit of statistics.
Yeah, so I thought, okay, cool, let's take that plot and then let's try and explain a little bit more about it, since it's TidyX, or explain it in a different way. And so the way I wanted to do this was I wanted to, I'm going to define what I call estimated true win percentage, or adjusted win percentage. And I'll walk through this here a little bit. The first thing that I need to do is get a vector of win percentages for all teams, and I set the limit here at teams that played at least 10 matches. I can't remember why. I think it came from the quantile of how many matches there were, but I can't remember why I selected 10. There was a reason for it that was somewhat defensible, though probably not if I wanted to publish it.
But you want to remove teams that didn't play a lot.
Yeah, exactly. So we've got a win percentage vector there. It goes 2,879 win percentages over time.
We've got 3,879.
What's that?
We've got 3,800.
Oh, sorry. Yes, that's right. 2,879 plus 1,000.
Yep.
So just calculate some simple statistics here, mean and standard deviation, something everybody knows. So the average for this population is right around 50%. Maybe that's like we would or would not assume. I don't know enough about beach volleyball to know if that's reasonable, but 50% is what it was, with some level of variance. And so obviously the standard deviation here is about 0.14 or 14%. So just like Ellis talked about earlier, when we looked at that plot, we saw that there's a considerable amount of variability with these teams when they're just starting out until they sort of settle in. And this happens in all sport. It happens in most things in life. There's a learning effect in different tests. And just like in sport, there's a performance effect where performance can be random, or people can start out really positive. So, for example, we looked at the team that was in blue there. I think it was Elaine Young and McPeak. And they started out really well. And so let's say they won the first 7 out of their 8 matches, giving them, right around like an 88% win percentage. Well, we wouldn't assume automatically after just seeing 8 matches that they're just as good as Kerri Walsh and Misty May. Like, there's just no way, right? It's such a small sample size. So one of the ways to handle this problem is to basically try and adjust the win percentage towards some sort of known value, or in this case, we'll use the mean of our vector of win percentages there. And the way we do this is we're going to use what's called the beta distribution, which is a useful distribution when we're dealing with outcomes that are successes and failures, or in this case, wins or losses. And so I wrote this little function here, which helps us define the parameters of the beta distribution. So the normal distribution takes parameters of mean and standard deviation, or mean and variance, rather, right? And so that defines the shape of the normal distribution. In the beta distribution, we're dealing with successes and failures. We're dealing with an alpha and a beta parameter that help define that distribution. So what I want to do is I want to take the average of our win percentage column there, and I want to get the variance of our win percentage column. So if we just remember from basic stats class, the standard deviation is the square root of your variance, so we can get the variance by squaring our standard deviation. So if I feed both of those into my beta parameters function there, we do a little bit of math to get us these two values, alpha and beta. And so there we just tried out the function, and it produced these two values. We can use those values later on, and so we'll store them in their own elements there as they're named, alpha and beta. And then we can just check to see if they actually are defining that win percentage vector that we had before. So if we do alpha divided by alpha plus beta, we get something that resembles the mean of the win percentage vector. And similarly, we can calculate the standard deviation and take the square root of it and get something that should look like exactly the standard deviation that we saw in the win percentage column. So this is going to serve these alpha and beta parameters within this beta distribution is going to serve as what we'll call our prior. So if a team wins the first 7 out of their 8 games, we're not going to assume automatically that they're an 88% win percentage team, but rather they're going to be constrained or drawn to the mean. And similarly, if a team comes out and lays an egg and let's say wins 1 out of their first 8 games or 0 out of their first 8 games, we're not going to assume that they're a 0 win percentage team. Rather, they're going to be constrained up to some level towards the mean of the population, 50%. And as they play more games, this is how Bayesian updating works, as they play more games, their observed win percentage begins to constrain towards their Bayes adjusted win percentage, and we get a better idea of who they are. And like I said, there's ways of testing how many observations we need to see to feel confident about that. So we've prepared our beta distribution. We can actually plot it and look at what it looks like. So it looks kind of like a normal distribution. If we were to plot the histogram of the win percentage column, it's going to look similar to this, or we could plot histogram or density of the win percentage column, either one. Both of those are going to look similar to the beta distribution, which is, you can see there in that plot call, I define it from a sequence of values from 0 to 1, right? Because the outcome is binary, so it has to be bounded at 0 and 1. And so I take this long sequence of values between 0 and 1, and with what I put on the y-axis there using the d beta function, I get the distribution between those values, 0 and 1, defined by my alpha and my beta parameters, my shape 1 and my shape 2 parameters. Okay, so now that we have that information, we can go ahead and create this adjustment to the observed win percentage. So that's what we do here. So we take our team outcome data and we make sure that it's arranged properly by the team and the observed match number that they've gone through. And we create an outcome ID, which is basically just a series of 1s or 0s, whether they won or lost. And we group by team. And we create a cumulative match number. So it's just sequencing along, basically counting from 1 to n number of matches that each team has played. We get their cumulative wins, which is what we calculated above. We get their alpha value. So this is how you update your little empirical Bayes model there that we've created. You have an alpha and you have a beta parameter that are sort of our priors. Those are our starting points. And we update them with the alpha or the wins, the successes that the team has. And we update the betas with the failures that the team has, which in this case is going to be match number minus wins is going to give us losses. We get the unadjusted win percentage, which is going to be the cumulative wins, the observed wins over the observed match number. And then we get our Bayes adjusted win percentage, where we're taking the team alpha that we calculated above and dividing it by the total number of trials, the team alpha plus the team beta. Mm-hmm. And then we calculate our variance of that distribution right there. And then we calculate the standard deviation by taking the square root of that variance. So if we run that, we get a data set that gives us some columns at the end. So there you can see, for example, the first one right there. So that team went out, and in their first game they won. We don't assume that they're a 100% team, obviously. We know that our initial prior was at 50% was average. So right now we're assuming, okay, this team might be a little better than average. And as they play more, you can start to see their. So that's a team that only played 2 games. The next team played
2 teams.
1, 2, 3, 4, 5. So you can see them how they start out with a win. So they're a little bit above average, then they take a loss, so now they're back down, then they take another loss, so now the model's thinking, okay, maybe they're a below average team, and it just kind of goes on from there. And so we can actually use this and plot this, and it actually comes out with some interesting plots of observed and adjusted win percentage, and that's what we'll do right here. Yeah. So why don't you walk them through this plot there?
For sure. All right, so we take this team outcome Bayes, which is containing all that information just calculated there, and we are looking at Kerri and Misty, unsurprisingly. All right, so we're going to send that filtered data that only contains their games in there, and we're going to send it into our ggplot. We're going to define our aesthetic. This time, all we're defining at the very beginning is our x-axis, since that's going to be the same across all of our geomes, which is the cumulative match number. Next, we're going to draw a geome H line, which is going to be drawing just a straight line all the way across, so horizontally, so that's H line. And so we're going to set the y-intercept to be 50%, and it's going to be line dash. So that's just a reference line that we're going to be looking at. Next, we're going to be drawing our geome line, and so this is the actual win percentage for Kerri and Misty over time. And so this is our unadjusted win percentage. It's going to be the same value that we had earlier in that rolling win percentage that we calculated in one of the earlier plots there. Next, we're going to be drawing the geome line, and this is our Bayes adjusted win percentage, and we're going to define this column to be red, or excuse me, this line to be red, so col equals red. One thing that we thought might be interesting, so we added it in, is adding some uncertainty to it, because we don't necessarily know the Bayes estimated value isn't a point estimate necessarily. It's a distribution. They're like, it can be anywhere within here is what it's thinking it could be. At least that's how I understand Bayes. So what we're going to do is draw these geome ribbon. So this is kind of like drawing an area plot where you're going to say, okay, along the x-axis, fill in between these 2 points. So that's what the y min and y max are. And so I'm going to draw 2 standard deviations and 1 standard deviation out from the Bayes actual point estimate to draw in our uncertainty. So I don't remember how much 2 standard deviations covers. Is that 3 sigma is like 99.99?
Yeah, it'll be about 95% of the data will fall within 2 standard deviations.
So it's expecting that you're 95% confident that, or 95% chance that
95% of your data of the distribution of this data is going to fall within 2 standard deviations of that point estimate.
Gotcha. All right, so then we're gonna. So that's what these geome ribbons are doing here. We're going to set their alpha, so how clear they are to see that this 2 standard deviations were not as, it's not as much of a point estimate, so I'm going to draw the alpha to make it a little bit more see-through. We're setting our y-lim to be between 0 and 1, so that it encapsulates all the potential information of the win percentage. We're going to set our labels. The match number is X, the win percentage is Y. Defined our title, Walsh, Jennings, and May-Treanor, rolling win percentage. We're adding our subtitle. This is where we're going to be defining our color.
Color of the lines,
yeah. Rather than doing a legend, we decided to do it this way. Oh, excuse me.
Uh-oh.
Get out of there. Because of the way there's a bug right now where things. Oh no! What's going on? You're working before call graphics invalid graphics state. Well, this is doing it live, so we're going to just restart and run down again. Give it a second, let it get all the way through. Thank you all for sticking with us for this long. Rounding out 54 minutes or so.
Oof.
Appreciate you sticking with us. So let's run that. There we go. All right.
All right, sweet. Now it looks, that's a nice looking plot.
Yeah. So as you can see, that black line is the observed win percentage over time for Misty and Kerri.
Yep.
Then you can see that red line here is the Bayes estimated win percentage over time. So initially, at the very beginning, they won several of their matches, but it's like, I'm not so sure about that. We don't have quite enough data to say that you're that good.
Yeah.
But then over time, it's going to somewhat follow that trend line as well. Or like what they
over time they begin to converge. It's the classic, like you learn in Stats 101, sample size matters, and the larger the sample, the more kind of sure you are of what you're observing, whatever the effect that you're testing is. And so in this case, as the sample increases, the more certain we get that this team is really, really good. And so obviously, confidence intervals are dependent on sample size and things like that. So our certainty about the team begins to shrink and get smaller, and what we observe and what we estimated or adjusted for begins to converge. And so, after about, it looks like after about 100, 200 for sure at 200 matches, we were certain that this was a pretty special team.
Mm-hmm.
Yeah,
for sure.
Pretty cool.
There you go. And it just continues to narrow down, and because it's constrained to this distribution, it's always going to be. This is one thing that I asked Patrick about as we we're looking at it initially. It's always going to be a little bit lower in this case because they're above the average.
Yeah, if they were a really bad team or below the line, it would be trying to always pull them up towards the mean, unless it saw 800 games of like horrible play and they were like a 10%.
Yeah, then it's like, I'm not so sure.
Yeah.
Like, are you sure this is your sport?
Yeah, exactly. That's more what it's telling you. So we had that, and then we also had one other. That was the distribution. So
yes,
like Ellis said, it's not just about reporting or providing a point estimate. So there's point estimates are ways of summarizing a distribution, right? So they're ways of basically giving people a single value, usually the most likely value out of that distribution. But it's important to remember that there's an underlying probability distribution underneath that point estimate. And so to kind of evaluate that, we can look at two teams and how good they are relative to each other based on how much overlap there is in their distributions. And so for this last plot, all I did was we take the team outcomes data, we obviously filter by the two teams of interest above, we group by team, and we calculate out their wins and losses. And then I add in this crossing function here. So basically crossing is, I think in Bayes Theorem it's called expand grid, but the idea is that it's going to find every permutation of every row from whatever I put in that crossing function. So in this case, it's 1 to 10,000. And I called that NSIM because we're going to use that as a simulation of the underlying beta distribution for these teams. So we create a very, very large, long data set with 10,000 rows for each of those two teams. And then we pump it through this beta simulation where we use the R beta function, n being the number of simulations that we want. And the shape being alpha and beta plus our wins and losses observed for that team. And then we do a little bit of plotting here where we have on the x-axis the beta simulation, and we use a density plot filled by the teams. So we get two separate density plots with some level of opaqueness, alpha equals 0.5. I specify the x limits there because if it goes from 0 to 1, it'll be really small since these teams are really weird looking, and compressed since these teams are pretty far from 0. And if we run that, we get an a density plot that looks like this, where we see one team relative to the other. Obviously, if we were looking at just point estimates, we'd think that the team in green there, Lambert and Metzger, are better than Patterson and Gibb. And indeed, for whatever number of observations, I think they played less games, so you see a larger distribution than Patterson and Gibb, who played more games. Their distribution is a little bit tighter around the mean. But obviously, there's a considerable amount of overlap that we can see because of the opaqueness that we provided. So we could do other things with these types of distributions, like we could do some sort of probability of the winning team given previous success and things like that. We could almost do like a matchup generator where we generate the probability of one team beating the other and stuff like that. But yeah, so that's what we got today.
All right. I think that was a very quick crash course in Bayes and how you can use that to
yeah.
explain
Cool.
by us. And then we've got a Shiny app at the end of here. Those of you that want to go through our code to see how to do some Shiny stuff with this too. So we've got some extra code for those of you that want to do that. So
Yep.
Yeah, but thank you so much for sticking with us for this hour long. I think this is our longest one so far. We didn't intend on that one. Once again, you can find, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name's Patrick Ward. You can find me on Twitter at OSPPatrick. And you can reach the both of us with questions or comments or thoughts and things you'd like to see at tidy.explained@gmail.com.
All right. Thank you, and keep on exploring your world.
Boom.